All right, so we're going to be talking about functors and the function type today. So we left off talking about the type class monoid yesterday, and you have heard now a lot of other things about monoids from the category theory talk, and also Ryan mentioned them in his talk. So we should all be pretty good with what monoids are, right? What's a monoid?
Empty, right?
Yes. Yeah. So we have a type class named monoid, and monoids are types that implement the monoid type class, right? Are instances of the monoid type class. So they have an identity value that we call empty, and they have a binary associative operation that we call append, or we write with the two little angle brackets. All right, so the instance is the piece of code that ties a type class declaration, such as the one we just saw, to a particular type. A type class declaration is as polymorphic as it can be to be flexible enough to work with many types. And an instance gives the implementation for a given type. So we were talking yesterday, I have cleaned these up a little bit so that we don't have to talk about, S times and if there's constraints on n. So I cleaned these up a little bit. So remember we were talking about how integers form monoids under two operations, multiplication and addition. They share some similarities, and those similarities are what we're talking about when we talk about monoids, right? The binary associative operation with an identity element. But the differences mean that we have to have two different ways to implement them, to implement that operation. And so what we do in Haskell is we give the types new names in order to have two different implementations. So we have the product type is a different name for an integer, or actually a bunch of other numeric types as well that form a monoid under multiplication. And we can write the append operator then is equal to the multiplication operator, more or less. I took some things out of there. If you look at the code and base, there's some things that I have removed. But it's more or less equal to multiplication. And then we give it, for our monoid instance, we give it an identity value, or the empty value is 1 wrapped in this product label, right? Because it's no longer just any integer, it's an integer under the multiplication monoid, so it has to be product 1. Thank you so much. All right, so we have given it a different name so that we can have this multiplication implementation and another name for the addition implementation, right? This is a new type name for, yes?
Is it in this case so that you constrain the type of none? So what happens if you have a sum of something else? Right. You have a new type sum A.
Yeah, the A has to be
right, but what I mean is you can still instantiate it with something else, and in that case it's not an instance of these classes.
You can instantiate some like on a string or something?
Yeah.
No, I think, no, they have to be a null.
Right, okay.
Yeah. Huh?
Yeah, let's just wonder.
Yeah. Huh? Yes. Yeah. Oh, yes.
Okay.
Yeah.
It's a bit confusing to me too, like when the known constraint is on the monoid instance, but it's not present in the data or the new type declaration.
Right. So, yeah. Does anybody ever actually use product and sum? Because product and sum are a little bit weird because we have addition and multiplication in num, right? So there's not really any reason for the product and sum types to get used, I think. Does anybody ever actually use them? Yeah, I've never actually seen the product and sum types like in real Haskell code. So they do exist in data.monoid, but they are a little bit weird. So it is a little bit confusing. But yeah, there would be a num constraint. Like the A in sum A has to be constrained by num. Does that help? Okay. All right. So, did I skip a page? No. Okay. Right, and so as I mentioned yesterday, semigroup, since it's now actually superclass is monoid, as you can see here, not there, there, right? The append operator is actually coming from the semigroup type class now, and just the mempty is in monoid. But I still refer to these as monoid instances, I guess, out of habit. All right, so type class definitions are as polymorphic as they can be, right? The declaration of the type class itself, and which is only type signatures, and they're as polymorphic as they can be. You can put constraints on things in type class declarations. We'll see some of those in a bit. But append, this operator, doesn't work with just any type in the universe, right? Because it's constrained by the monoid type, or the semigroup type class itself. So it'll only work with types. That operator will only work with types that have an instance of the class semigroup. Okay. Okay. All right, so how do we know if a type has an instance of monoid or semigroup? We either look it up, right? You can query in GHCI to see if it has an instance, or we could write one if we know it doesn't, right? Like if it's a type that we created, and so we know that we have to give it an instance of semigroup or monoid. You can derive them sometimes. But how does the compiler know if there's an instance available? Right, compiler is compiling your code, and it sees, you know, this operator, these two little angle brackets. So how does it know if there is a semigroup, and if so, what the implementation should look like?
Well, you wrote it, right?
Well, someone wrote it. Or someone derived it. So it looks it up by the type name, right? So the instance that it's looking for, right, it looks it up by the type name to see if there is an instance in scope. So if you've used some maybes, for example, if you've used some maybes with the append operator, it will, you know, it looks up to see if there's an instance of semigroup and monoid of the maybe type in scope. All right, so when we evaluate something, so we have here, this is what's called GHC core, this output here. Okay. So this is what's called GHC core. It's the first step in the compilation process. This is a very cleaned up version. You get a lot of other stuff in here if you just look at core output, but I have suppressed a lot of the things that core would ordinarily be showing you so that it's less noisy. So if we try to evaluate the expression 5 equals 5, then this is the first step in our compilation process. Now, if you look in GHCI, right, the double equal sign has an eq constraint on it, right? Because the two arguments to the double equal sign have to both implement the equality type class. So it has an eq constraint on it when you look at it in GHCI. The first thing will say eq a, then a to bool. So we see here that it equals the double equal sign, and then it tells us which eq instance it's using. The eq instance for integer. It's already gone and defaulted, right? We looked at how 5 could be 5, even though it's a numeric literal, is polymorphic, right? It's a num a to a. But it's already gone ahead and defaulted to integer, and it's using the eq instance for integers. And then we see in the next line, print has a show constraint on it, on the first argument to print, and it's gone ahead because eq returns a bool, so what it has to print is the bool, and so it's given us the show instance for bool. Does that make sense? Okay. So it looks up the instances by the type names. All right, you can get a GHCI that shows you core output that looks like that, by doing this. You can see how many things are suppressed here. You can remove these suppressions to get a much noisier core output, which can be fun. All right, so types and type classes form a system linked by instance declarations. A slightly different operation, such as the difference between a monoid and a semigroup, means that we give it a new type class name. That's a different type class, right? Semigroup and monoid are different type classes, because there's a slight difference in the operations. Semigroup is just a binary associative operation. Monoid is a binary associative operation with an identity element. So those are two different type classes. But for different implementations of the same abstract function, such as append, we have to give the types new names. Does that all make sense? It must. Okay. So we are here to talk about functors, and we are getting to that quite rapidly. All right. So there's only really two things that matter in Haskell, right? Types and functions. Nothing else matters. Huh? All right. But type constructors are functions that make types. Data constructors are functions that make values of a type. And the function type constructor itself makes functions that are values. All right, so now we're going to talk about the function type. Functions are a product of two values, sort of like tuples. And in fact, the data declarations look very similar. So the data type for functions is data with the function arrow A and B, meaning that we have two parameters. These are type parameters, right? So it has to be applied to two type arguments. They can be the same. They might be different. So it's often said that functions in Haskell always take one argument and return one result. So we can see that in the type. They take an A and they return a B. All right, the second line after the data declaration says that it's an infix operator. Infix R means that it's right associative, and the 0 is its precedence. So that's the lowest, right? Isn't 0 lowest? Okay, so infix operators like plus and double equal sign and the function arrow do not have parentheses around them when they appear in their infix positions, like you usually see them in type signatures. But we do have to put parentheses around them when we use them prefix, or when we're asking for their information in GHCI or something. All right, so that means that this thing on the top, right, function arrow A, B is the same as A function arrow B. Okay. So, of course, A and B can themselves be functions. And so a function can accept a function as an argument and return a function as a result. All right, so the arrow is a type-level infix operator that associates to the right, which means that this type signature for max can be reparenthesized like the way you see it on the bottom. It takes in one A and returns a B that is a function from A to A. And we'll then take in a second A, right? It then gets applied to second A, just like the lambda calculus, right? Okay, and then finally we'll return an A at the end. All right, so that's why we can write functions like A to B to C to D and still say that we have one argument and one result. Now, colloquially, right, we refer to that as a function that takes 3 arguments. But underneath, that's not what's actually happening, right? It's actually a function that takes an A and returns a B to C to D function. Then it takes a B and returns a C to D function, and so on. All right, we don't need those parentheses, the parentheses around B to C to D. We don't need those parentheses because Haskell is curried by default. As a further aside, function application is left associative, right? The function arrow is right associative, function application is left associative, which so that a function applied to x and y is really first a function applied to x, and then the result of that applied to y. So that's how we have the ability to partially apply functions and then pass them around, right? Give them new names, right? Pass them around. Does that make sense to everybody? Okay. All right, so the default currying is why these type signatures do need parentheses, right? Because the first argument to the dot and the second argument to the dot do have to be functions themselves. And the first argument to flip has to be a function. So those parentheses are not superfluous. The ones that we had like around the A to A and max, those ones are. All right, so if we took those parentheses off, we would have, right, this whole thing, and that's not what we're wanting at all.
So
Yes?
that's due to the right associativity and not to the currying, right?
Yes.
Okay, so it's not the currying that it's set to.
Yes, right. Okay, so back to the function type. The function type itself has these type class instances in base. Right? These are available in the prelude. We are not going to talk about the monoid instance at all, and really we're going to not talk about the applicative and monad probably at all. It's the functor instance that we're going to care about. Okay? But these are the ones that it has available in base. I think I'm going to have now way too much caffeine. All right, so finally let's start talking about functors, unless we have any further questions about what we've talked about so far. Awesome, you guys are great. All right, so let's look at or possibly sleep. So we have this is the type class declaration. So we have seen the monoid type class declaration several times. Functor here is a type class. Again, we have the one method type class. There are some other methods in the functor type class, but this is the only one. An implementation of fmap is the only one that is required, and all the rest of the methods that are in the functor type class can be derived from an implementation of fmap. So this is the only one you actually have to be sure that you have. So we're going to talk about this. F has the type star to star. We're going to be talking about that. So if you're not familiar with that notation, don't worry. So it says we have a class functor, F, where fmap has the type A to B to FA to FB. So the F here is our functor. All right, so functors in Haskell are type constructors that have a lawful definition of fmap. Right, that F that we call a functor in the fmap signature, that F is the functor. All right, so some types. Now we're going to get to talking about the stars. Have all of you seen the stars before? When you go out at night.
Exactly.
So some types are concrete or nullary constructors. So we talk about how type constructors are functions that construct types. Some of them don't actually take an argument. Like bool doesn't take an argument. Int, characters, right? They don't take any arguments. So in some sort of trivial sense, we still consider them to be functions that construct a type. But since they don't take any arguments, it's really sort of silly, and so they're concrete types. Yeah, I guess if I wander to that side, it's hazardous getting back here, isn't it? All right, but many types are parameterized. So many of them do take at least one argument. We have on the top maybe, which we've seen. Maybe takes one argument, one type argument, and the type argument shows up in the just value. Either takes two. List takes one. Although, since it's recursive, it can keep taking more and more A values, but they all have to be the same type. Tuples, take 2. So if it's a pair, you can have 3 tuples, 3 triples, triples. That would be A, B, C, for example. You can have them, I think in base we have them up to something like 64. So you can have a tuple of 64 elements if you're really feeling wild. And then there's the function type. The function type doesn't have any data constructors, or at least not ones that we can see. And so it has 2 parameters and like a tuple. So the 3 on top, right, maybe either in list or all sum types, which means that only one of those sides shows up at a time, just like bool, right? So a maybe is either nothing or just A. And either is either left A or right B. A list is either an empty list or a list with some elements in it. But the product types on the bottom, the tuple and the function type, they both have to have both of those arguments before we can construct anything. All right, is that all clear? So we have these parameterized type constructors. All right, so type constructors are functions that make types. So maybe itself has the kind or the type to type. You apply it to one type argument and it makes a type. If you have maybe string where it has been applied to a type, then you have a type. So maybe by itself is not a type, it's a type constructor. Maybe string is a type. Everybody's nodding. You guys are awesome. All right. So we actually call those kinds in Haskell, and kinds are the types of types. And that's what those stars are. So we would actually say maybe has kind star to star, and maybe string has the kind star. So concrete types, like maybe string or bool or characters, those all have the kind star. So that's what that star to star meant in the functor type class definition. It means that the F has to have the kind star to star. So it has to be a type constructor like maybe that needs to be applied to one argument before it can be a functor. Or I don't mean that it has to be applied to its type argument before it can be a functor. I mean it has to be a type constructor to be a functor. Does that make more sense? Okay. So some type classes, like really monoid is a type class for types, and some type classes are type classes for type constructors. So for example, we have another monoid, another monoidal, let's call it, type class called alternative, and alternative is a monoid for type constructors. So monoid and alternative are in some ways the same and in some ways different because alternative can't be used for concrete types, and monoid is really a type for concrete types. A type class. But functors have to be of type to type. So they must be type constructors with one parameter. All right, and then those type constructors must have a lawful implementation of fmap. And we know that we can read the type signature of fmap because of the associativity of the arrow as being a function from A to B that gives us a function from FA to FB. So it takes the function A to B and lifts the whole function into an FA to FB function. All right, and since we also need to apply, when we're actually using fmap, we do have to apply it to the first FA. And then that's how we know which instance of fmap we're using, right? Because then we've given the F a name, and then the compiler can look up which instance we're using. Okay. Oh, I thought the diagram was next. All right. Fmap gives us a way to apply a function to a value, or values in the case of lists, that is inside some other type. So if we fmap +1 over a list of 1, 2, 3, because list is a functor, then we can apply that function inside the list. We can do the same thing with maybe values, because maybe is also a functor. So we can apply the +1 to the 3 inside the just, and return a value. So it lifts that +1 function into either the list context or the maybe context. Right? The numeric values there are not functors, but the list and the maybe are. All right, so here you can see a visualization of why we call it lifting, right? I've just borrowed an image from another slides that I've made. And we have F that has the kind type to type. We have G, which is a to B or an A to Z function. And fmap takes the A to Z function and gives us an FA to FZ function. So the G function from A to Z is the arrow on the bottom. The F's are type constructors that get applied to each side. And then the top is the fmap G, where fmap G has given us FA to FZ. So this is why it's called lifting. Any questions?
Can you maybe make a practical example now?
Practical example of?
Yeah, like instead of having a G having what it is original.
Well, do you mean you want me to annotate my diagram with types instead of letters?
No, I was just wondering if an example of that for G or G that could.
So here, yeah. So in this case, what we were calling F on the diagram, which was the functor, right? In the top example, the F is list. Yeah, and in the bottom one, the F is maybe. The G function in both of them is +1. So it's taken that +1 function and lifted it into either a list of each element +1 or a maybe value +1. Does that make sense? Okay. All right. So for example, and here this might help answer your question as well. So if we get the type of fmap applied to maybe, we see that it takes an A to B function and gives us a maybe A to maybe B function. The way we write the instance for this is we'd say fmap any function, the underscore there is just our otherwise or our any function case, right? So fmap underscore for anything, whatever function that might be. If we're trying to fmap it onto a nothing, then we get nothing. Right? There's no value there there's no A value to apply an A to B function to. Right? So we just have to return nothing. If we fmap a function and then just X, we're going to lift the function into being a just A to a just B. And so we'll return just function X with the function applied to X, the A to B function applied to, or X, let's call it, X to B function applied to X. Does this make sense?
Just the at symbol? Is that something?
So the at symbol, I should have put that on this slide. I have a slide coming up telling you how I did that. It's a language extension called Type Applications. You can enable it in GHCI, for example, to see the type of things like this, and I'll show you how it works in a future slide coming up. It has actually a lot of other uses, but it's really handy for doing things like that in GHCI to see what the specialized type will be. Okay. All right, so we've said that a functor has to be of type to type, meaning it has to only have one parameter. But we've seen that things like either and tuple and the function arrow, right, have two parameters. They're type to type to type. So you can see there that the kind of either has 3 stars. Star to star to star. So we have to partially apply it to something, to its first argument, because function application is left associative. So we have to apply it to its first argument to be able to turn it to make it into a functor. So when we apply it to its first argument, that's the second example on the slide, kind either underscore, meaning we don't care what that type argument is. It's irrelevant to us right now. Then now either underscore has the kind star to star. Now it can be a functor. Does anyone have questions, or do you just want me to go on?
So I suppose that explains why when you fmap, either you fmap direct because it's second, right?
Yes, exactly. So what he's saying is, because I guess he's seen this before, let's get GHCI open here. And if we fmap our +1 function, like this, over a left value, it just gives us the value back and it doesn't apply the function. Because that first argument is part of the f. We've had to partially apply the either in order to make the functor. You'll see this a little more clearly when we work on the instance. So if we have a right value though, then it can apply the function. Okay.
So we could define an fmap which works on the left.
But we would have to define a different either.
Yeah, because the names, I mean, left and right, they don't have to be in that order, but it's always going to have to be the leftmost type parameter that you apply it to, because function application is left associative. But if you wanted to define an either that looked like this, let's call this either alternative. Then you can make a functor that works with the left. Mm-hmm. Because now the b that's in the right is actually the leftmost type parameter. Mm-hmm. Does that make sense?
Mm-hmm. Let it sink in.
Is there like a type level flip in Haskell?
Sure.
So you can just flip the either. Then, I mean, it's like you have flip for functions to switch the order of the arguments. You have something to switch the order of the arguments for types?
At the type level? So like before the either, you mean?
Yeah.
I don't think so. Do we?
I don't know.
I'm not sure.
I'm just asking.
I mean, I'm surprised that language extension doesn't exist, to be honest, but yes.
I'm not sure about the flip, but allowing for an arbitrary lambda for type
Yes.
parameters makes the compiling undecidable.
Yeah, probably looking at Scala.
Yes. Yeah. So, but you could do this, like if it was the left that you want to apply a function to and you want to ignore the right-hand values, you could flip the order of the arguments. But since function application, and since either is a type constructor, so it's a function, and so function application being left associative, the leftmost is always the one that has to get ignored. With functor type class at least. There are other ways that we'll get to soon. All right, so now we can make now we can make a functor instance for either applied to its first argument. And that will look like this. We'll have the a to b function still. Then we'll have an either. It's GHCI has given it the name t, but it just means it's some type that we don't know and we don't care. We're not doing anything with it in our function. And then you see the a, right, either TA to either TB. The a and the b are the ones that are part of the a to b function. The t does nothing. It's just getting passed around with the either. Does that make sense? All right.
What's with that at sign?
Yeah, that's what he just asked a minute ago about maybe. So that's a language extension called type applications. Let me see when I actually get to that in the slide. Way after I've actually used it. Sorry. Right there. There I show you how to actually use it. So if you in GHCI, you can turn it on like other language extensions, like at the top of a file, language type applications. But you can also set it in GHCI. And then in GHCI, then if you ask for the type of some function applied to a type, like maybe, then it gives you what the applied function looks like. Sorry.
Okay, I see.
Yeah.
So you're just treating the type constructor like a function and passing types to it.
Yes.
Okay.
Yes. So, sorry I was using it without putting this in there first, but this is something that you can turn on and use. It can be quite helpful. There are other uses for it. In fact, I believe when Sid is talking, you're going to show us some. You're going to show us some type applications?
Many type applications.
Yay! All right.
So it's just like you pass whatever there, right? Because
Yeah.
there's underscore, right?
Yes, I'm just passing with either. I'm just passing whatever to it because we have to partially apply either. Like if you try to do fmap at either with no argument, it'll tell you that that's the wrong kind.
Yeah, because you still have two.
Right, because you still have two arguments. So you have to give it some argument. And GHCI will complain if you try to put like an A there.
Yeah,
It will complain that the variable's not in scope.
Right.
Yeah, so if you just put an underscore, then it works.
Dumb question. Oh, well, it's nothing.
No, go ahead.
Okay, because you can have like for all at type level, right?
Yeah.
But it's not type level, so you can do for all A and use A then, right?
Maybe. I haven't tried,
Okay.
but maybe. I have not tried that. Okay, so we're going to now write in either instance for functor. Some of you, I'm sure, have done this or actually seen what it looks like before. So our type, the type of fmap for either looks like this. We take an A to B function. We have an either T, A, and we return an either T, B. Do you want to remember what the maybe one looked like? Or you got this? So what will the implementation of fmap look like for either? If you really feel like you have no idea, then just take a couple of deep breaths and we're going to walk through it in a minute. So it's all good.
That's just one thing that is confusing about this.
Uh-huh.
I know it's common right now, but you have the A and you were using it in there's no relation then.
There's no relation. Yep. Yeah. I usually change that to be T or X or something where people will not worry about the name, but yeah, there's no relation.
Yes,
All right, so the first line of it should look like the first line of the maybe instance, where if we're trying to fmap a function onto that left value, we're just going to return left x, right? Because we don't have a value that we can apply the A to B function to. So that's what the first line should look like. You could use an underscore there instead of the word function if you prefer. I think that's how I had the maybe one. And you remember, it wasn't very long ago. I was just commenting earlier to Chris. It wasn't very long ago that thinking about writing functions just freaked me out. I thought this must be so hard, right? Because I mean, this is in base, right? Ooh, must be super complicated. And you just think for a minute what must happen with the right. All right, so what must happen with the right is that we just apply the function to A. And if we have that right A, and we've got an A to B function, we apply the function to A, we return our B, and we get a right B. Does this make sense to everybody? Cool. Okay, so we've been talking about the functor type class and this function fmap. If you do have questions, like if I'm moving too fast, just feel free to stop me anytime. All right, but there are other ways of lifting. So we have the functor type class with its function fmap. We have the applicative type class with its function the TIE fighter. We have the monad type class with, and I've given you here what we call flip bind, which is a backwards bind because its type signature is more similar to the type signatures from functor and applicative. Okay. Usually when you're looking at the monad type class, you're looking at the bind that goes the other way. That is part of the Haskell logo, right? The two pointers going the other way and then the equal sign. But bind, for some reason, has its arguments in reverse order. So we'll look at that in a bit. But you can see the similarity between these three functions. Right? If we line them up like that, you can see a lot of similarity between these three functions. So with applicative, we still have the FA and the FB on the end, meaning that those Fs are the applicative Fs. Functor is a superclass of applicative. And so, oh no, I never got the diagram. All right, functor is a superclass of applicative, and so those Fs in the applicative type signature are also functors. They also have an implementation of fmap, and you can see why they must. Right? This is really very similar to what we just did with fmap, right? So for now, there's another F on the outside of the function.
Why?
Well, because sometimes you end up with just function, and you want to apply it to another just. And I know it doesn't seem like that's probably a thing that ever happens, but it does. We're not really focused on applicative and monad, so I don't have a lot of examples of it here, but I do have some I could show you. Okay. So it does happen sometimes, and that was found to be a useful and helpful thing, and so now we have a type class. Applicative didn't used to exist. Applicative is new in Haskell. So we had functor and monad for a long time, and then they discovered that there was this sort of intermediate thing between functor and applicative. Between functor and monad and applicative, and so now we've rearranged everything and put them in their proper order. So then we have monad M, which is sort of the big famous one that everybody gets upset about. But you can see it's really just another F map, right? Except for there's an extra M in there. And it is. It's just another F map, except for it has another method called join that lets us sort of smash two layers of M together. That's all it is. So these are some ways of lifting. All right. Oh yeah, see here. Here's the applicative spiel. Applicative type class is similar to functor, but it has some extra things. There's a method called pure. There is also a similar thing in the monad type class, although we're doing away with it. Have we officially done away with return?
No.
I don't remember. I think return is, huh?
There's the monad of no return proposal, but it's not very clear.
Right. So return is still there in the monad type class, but it's the same as pure. So now everybody just writes return equals pure from the applicative type class. Pure just takes a value and lifts it into an FA. Takes an A, lifts it into FA. So it takes an A, lifts it into maybe A, for example. Takes an A and lifts it into either TA. Right? Because just like functor, monad and applicative also take typed constructors that are just star to star. So we still have to be partially applying the either.
Can I? Or not?
What?
Question.
Yeah.
Why is it not in functor? Is it like a functor you cannot wrap anything into? Because so far as I understand, this takes something and wraps into the applicative, right?
Mm-hmm.
And don't you do the same with functors? You take something and put it into a functor? It's like a functor you can put anything into?
So functor type class, I don't think has a method like this, right?
I don't know, maybe.
Yeah. I think because I don't know what you would use it for. Well, because applicative, sometimes if you're doing a lot of things in applicative or with monads, especially if you're in like the IO monad, and you get to the end, and your ending thing is not in IO, and so you have to put, you know, return or something to just lift it into the IO monad so that it will type check. And so sometimes, like if you're doing things in applicative, you have one function that's not, and so you've got to lift it into the applicative so it will match all the other ones, and so you use pure for that. I don't know what you would use it for in functor.
I really
It
liked,
just doesn't come up in practice, right?
Yeah.
Okay.
I
Yes.
really liked in your book, I'll probably not say this quite right, but I think you say that the applicatives are monoidal functors.
Yes.
And the pure is kind of a little bit like writing the identity, right?
Yeah.
I thought. And so that's kind of one of the big differences between the functors and the
Yep.
I see.
Yeah. Yes. Any more questions? Okay. All right. So if we look at we're going to look at applicative and monad kind of quickly because they're not our main goal. We're trying to get all the way through. We're going to power through to profunctors, right? Yes. All right. So we're going to kind of breeze right through applicative and monad. Hopefully, everyone has seen them a little bit before because I didn't put in a lot of examples of them. So if we write an instance of applicative for maybe, the pure would be just, because if we have an A, we can't lift the A into nothing, right? Because it doesn't hold a value at all. So we have to lift the value into just, right? Just A. So pure would be A to just A. If we have, since this operator, I think most people call it apply, I call it typewriter, but since this operator takes a function on one side, and on the other side, it takes a value of FA, right? So with nothing, we again, sort of like with fmap, we don't have anything to apply a function to. Either if nothing is in the position where it should be a function, it's clearly not, right? And so we don't have anything to apply to the next argument. And if it's in the next slot, the FA slot, then we don't have anything to apply the function to, and so in both cases we have to return nothing. If we have just a function that we're trying to apply to just an A, then we have just function A. So you can see the similarity here still between this and our functor instance for maybe. Right? The only difference here really is that with fmap, we had fmap function just A, and it was just function A, right? Okay. So, and this is what the either applicative instance looks like. So, we're treating left x because the x is attached to the either, right? Because we have to have kind star to star. So we've been partially applying the either to its first A value. Right, this A up in the either A and this A and right A are not the same A. They have the same name, but they're not the same thing. So we've applied either to its first argument, in which case the left value that I've called x here is very similar to the nothing of maybe, right? There could be something there, but it's not something that we can transform through with a function application. That make sense? Do we remember why we can't transform it with a function application? Same reason as fmap, right?
The type stays the same.
Huh?
The type stays the same.
Right.
This is A.
Yes.
In the preamble.
That's right. The type stays the same because when we partially applied either to A, we sort of fixed that type. Right? That A can't change. Whereas an A to B function could potentially change the type, right? The A that there has been fixed. Okay, and so then the last line of it, right, we just apply the function to A and return it wrapped in a right. All right, monad is just another type class, the same kind of thing. It's just we have a different position of where the extra structure is, or the extra type constructor is. This time, instead of flip bind, I've given you bind, which does have the inputs in the opposite order of fmap. They're not different, right? This MA here, the first argument, is the same as the FA in fmap. So the extra bit that makes it monad, that makes the monad type class, is that with applicative we had an F on the outside of the A to B function. With monad we have an M on the inside. So for example, if we have a function that goes from string to maybe string, then we would have, and let's say we wanted to chain a couple of those together. So we have all these string to maybe string functions. And we would need to pass the maybe string from one to the string to be a string input for the next one, which would go from string to maybe string. And that's a monad. That's what this does. So this one is, again, very similar to fmap. The only difference is that inside we're producing more type, right? More of the same type. And then we return the MB just like we return the FB with fmap. All right, so yeah, this is where I finally got around to showing you type applications. I apologize about that. So the type of bind applied to maybe would be a maybe A, such as a maybe string, that we then pass to an A to maybe B function, and we return to maybe B. Same thing with either, but we still have that one type that I've given to type applications as an underscore, and GHCI has given back a T. And so we see which arguments are being transformed by the function here, right? Okay, and this is what the monad instances look like. With nothing and with left, we have the same sort of problem where we can't apply a function that doesn't exist if it's a left or if it's a nothing. And we can't apply a function to a value that is nothing or a left x, because that x has already been fixed as part of the either when we partially applied either. And we don't have to put a just, like when we apply the function to A in the last line, in the second line of each instance, we don't have to put the right or the just on the outside like we did with applicative or something, because now our A to B function isn't just A to B, it's A to MB, and so it's returning that M already, right? It's returning the just or the right as part of the function. Does this all make sense?
So if we were to do that, would it not type check, or would we get the value wrong?
I don't think it would type check. Because then really you'd be having, because bind is actually, this bind operator is actually made of fmap and a function called join. And join takes an M parentheses MA and returns an MA. And so you would actually be trying to give it an MMA. MMMA.
Just the type change.
Yeah, yeah. Is it break time? It's break time. But look, we got through monads. People.
We.
Come to order, please. Okay. Are we ready to get started again?
Sure.
Okay. We've covered socialism thoroughly?
Sorry.
Okay. I'm kidding. All right, so let's get back to talking about our type class instances then. So we've covered the fact that the function arrow is itself a data type. So, and we also noticed earlier that it does have some type class instances. And it has a functor instance, a monad instance, has an applicative instance, and we are going to talk about those next, because those are the path forward to understanding contravariance and profunctors. Okay, for our current purposes, we don't really care about the applicative and monad instances for functor, but you should check them out. I mean, for functions, because they are very cool, but we only really care for our purposes about the functor instance. So we notice that the function type has two parameters, like either and like tuples, right? And so it is kind star to star to star. So we already know that we're going to have to apply it to its leftmost type argument before we can have a functor instance, or an applicative, or a monad. So we will apply it to some unknown type, which we have again represented for the purposes of type applications, or for kindness, for kindness, yes. We have applied it to its first argument, and we have returned a star to star. So now we're ready to have a functor instance. Okay, so we will compare, right, the first line of our either instance, our either functor instance looked like this, and our function, the first line of the function instance will look like this. We're applying it to its leftmost type argument before we can have a star to star that we can make an F map for. All right, so we've also talked about the fact that when we use an infix operator like the function arrow in a prefix position, then we have to wrap it in some extra parentheses. So we want an F map for a function that looks like the top line, right? With our either F map, that function arrow t was either t, right? But it's the same thing. So we have an a to b function and a function of t to a, and we return a function of t to b. So we can take the arrow out of the prefix position and take those parentheses off and make it look more like a normal type signature, right? So now our F map for functions, take an a to b function as the first argument. For our second argument, we'll have a t to a function. Now t is fixed because it's the leftmost type parameter of the function arrow. And we'll return a t to b function. Right? So this is what F map will look like for functions. Now, we've seen a type signature like this before. Oh yeah, here's the diagram again, because now our F is a partially applied function, right? So the type to type, that F is a partially applied function. So we're applying the T to, right, the T arrow to each side, to the A and the Z, and lifting it up into transforming the G into an F map G, which takes us from the T to A to a T to Z. And it's the same thing that we saw with maybe and either. So we have seen this type signature before. We have seen this exact type signature before, right? Are these two the same or different? All right, some of you are nodding, but they're the same thing, right? The fact that some of the variables are named differently means nothing to us, right? So we have, nope. Nope. All we've done is rename some type variables. So now the T is in the same position. The T of the F map signature is in the same position as the A's of the composition operator. And we've gone T to A, which is our A to B function in the function composition, which means that the B's are in the place of the A's in the F map signature. But it's the same type, right? The names don't mean anything in terms of how the function works. It can be a bit confusing looking at this and trying to reason out which things, because we see the A's, and we want the A's to all be the same thing, right? We want them to all be in the same positions. But they're the same. So our instance for functor, for our partially applied function, is the same. Fmap is equal to composition. And this is always a time when I would strongly encourage people to take out pencil and paper and reason through this themselves. I don't have a whiteboard here, so we can't. So otherwise, I would do it myself. But if you look again there, and then there, it's all the same, right? So function composition is the functor, covariant anyway, functor of functions. All right, questions about this so far? Okay, awesome. You guys are awesome. All right, so while we don't usually talk about functor is just functor, right, when we talk about it. This is a type class for covariant functors. So next, because we're heading towards, I can't really see the hands on that clock very well. Okay, because we're going to be talking about contravariance. So we're going to get a handle next on what covariance means. So covariant functors are a way to express a relation between the outputs of functions. So, for example, when we talk about the covariant functor of functions, we're talking about the relationship between the outputs of two functions. A T to A function can be transformed into a T to B function with an A to B function. Does that make sense? All right. So that A to B function will take us from the output of the first function to the output of the second function. All right. So either AB is also a function that constructs a type. The covariant either functor gives us a way to go from either something A to either something B, just like we just saw with the functions. Right? So a right value that is A to either A, and a right value that's B to either B. That A to B function gives us a way to go between the either A and the either B. So those are covariant functors. I'm actually maybe going to finish with this part a little bit earlier. So the co prefix here, right? This confused me for a long time because I don't know if you've heard people talk about, co-monads, for example, or co-free things. So there's a co in mathematics that means that something is the opposite, right? So like in category theory, people will talk about product and co-product. Co-product means sum, right? It means the opposite of product or the dual of product. So there is a co that means the opposite or the dual of something in mathematics. And for a long time when I was trying to figure out what covariance and contravariance meant, I thought that the co, this was very mathematical, right? So I thought that the co was that mathematics prefix that means that something is the opposite. So I thought, so it's the opposite or the dual of variance, and then there's also a contravariance, which also then means sort of opposite. So I don't know what the heck is going on here, but it doesn't. It's a different co. Okay, it's the co that means together or cooperative. It means that they vary in the same direction, right? It means that the arguments all go in the same direction. So what does that mean? That means that the A to B function right? It's A to B, and then it's FA to FB. And so the A to B all go in the same direction. They cooperate. That's how I think about it now, so that I won't confuse myself anymore. Okay. So contravariance then does mean that they go in the opposite direction. All right, so that's covariant functors. We have one more type class to talk about before we go on to its opposite, contravariance. This type class that we're going to talk about, I think, will make him very happy because he really wants to apply a function to the first element of either and of tuples. So before we go on to contravariance, we're going to talk about another type class called bifunctor. If you are tired of having to ignore your left values, then what you want is bifunctor. Bifunctor is a type class for functors that are covariant in both of their arguments. And that's, in fact, all that the documentation says. If you look at the bifunctor package on Hackage, that's all it tells you. It's that it's a functor that's covariant in both of its arguments, but now you know what that means, right? It is something like either, where we can map two functions to get two different outputs. So now you can map to the left and to the right. So bifunctor is a type class that is really sort of two fmaps combined into one. It gives us the opportunity to lift two functions instead of just one for type constructors that have two parameters, like either or tuples. Okay, so here in this type signature for bimap, the P is the bifunctor, right? Just like the F in the functor type signature. So we take an A to B function, and we take a C to D function, and we take a P A C, so like an either A C. And we have an A to B function, and we have a C to D function, which means we can get an either B D. Now, bimap is the one method in bifunctor that is sort of required. It's the basic minimal requirement for a bifunctor instance. However, there are methods in the bifunctor type class that let you just map over one side or the other. Right and left. I think there are map and LMAP. Right? First and second? Which? One of those. Something like that. Anyhow, there are methods in the bifunctor type class that let you map over just one or the other. So then, if you want to just map over your lefts of your either, then you would use that, one of those. Okay, so we're transforming two outputs when we talk about bimap. All right, so for example, the bimap for either looks like this. We have an A to B function, C to D function. We take in two inputs, the A and the C, and we return the outputs, either B and D, or D. The bimap for tuples looks like this. We have an A to B function, a C to D function. We have a tuple of A and C, and a tuple of B and D as our return. Now, either and tuple are different, of course, because with either, you have one or the other value. With tuple, you'd have both of them. So, for example, we can use bimap here in our happy little greeting function. So we're going to partially apply bimap to two functions. Hello plus plus would be our A to B function. Goodbye plus plus would be our C to D function. Because with either, we have left or right. So we can't actually apply our greeting to both sides at the same time, because both of those values, left and right, don't appear at term level at the same time, right? But if we have a left, then we can still use our bimap, and it just ignores the second one. We have a right, it ignores the first one, and we apply just the second function, just the C to D, because that's the value that we have. We have a tuple, so I just left Switzerland, because I was at Zurich Hack. So I said goodbye to Switzerland and hello to Poland in one happy tuple. Okay, so that's how bimap works. So we always say when we're teaching people about functor, well, you can't have a functor for something like either that does map a value to that left side, but in fact you can. It's just called bifunctor then. All right, questions about bifunctor? I think bifunctor, once you've got the hang of functor, bifunctor is pretty clear. I don't know why People never cover bifunctor, I think, in beginner Haskell, and I don't know why, because it's just the same as functor. You're going to cover one, you might as well cover both, right?
Is this from the arrows package, or is it just?
No, bifunctor. Right?
I thought they put it in base nowadays.
Is bifunctor in base now? I'm not actually sure. I don't think it is.
Yes, it is.
It is?
They-
All right, bifunctors are now in base.
And last bit is that the end is the output, I suppose.
Huh?
You're doing another function call.
Yes. Right.
That would be hello phone. Is it just when you're taking the slides that I was wondering about last time?
What?
Before last time is the actual.
So this is the function application.
Yes.
Yeah, so greet is our function that applies hello to Poland.
Yeah. What
Yeah.
I'm wondering is if the last one is just
Yeah, the last one
that's what I mean.
Oh, yeah, sorry. Oh, yes. Yeah, sorry. That's just a typo. Sorry. Yeah, it would be, you're right, just like this. Yeah. Because it's the result. Yeah. Sorry about that. That's a bad typo. All right, any more questions about that? You guys are so ready for contravariance and profunctors. This is awesome. I didn't know.
How do they put that in place?
Huh?
Well, I'm just trying it out for me.
Just- To see if it's in base?
Nothing doesn't work. It just says it's not in scope by map.
Well, it wouldn't be in Prelude, but can you import?
Okay, so that's
Yeah.
Okay, so that's it. And so then you still have to import that. Okay.
Yeah. When does anybody know when it would have gotten in base?
It's base 4.8.
Which one is it?
Nice. So it's been in there for a while. So you'd have to import by functor, and then you should be able to. Yep, it is. It's in base. Profunctors aren't. I'm pretty sure, but bifunctor apparently is. So. Okay. All right, so profunctors, what we're going to talk about tomorrow, or Thursday, sorry, Thursday's the next time I'm up. So profunctors are bifunctors. So they have two type parameters. But they are contravariant in their first argument and covariant in their second one. So we've covered covariance. You're quite familiar now with what a covariant functor looks like. And we've covered bifunctors, so the only thing that's left to tackle before we get to profunctors is just contravariance. So, the reason that we spent so much time going through the functor instance for the function type is because things like either, well, we just saw that either is a nice bifunctor, right? It behaves covariantly in both of its arguments. Tuples are the same, but functions are not. Functions are not bifunctors, but they are profunctors. Because they are covariant in their second argument. We saw what that functor instance looks like. But they're contravariant in the first argument. We'll talk about that, what that means. Yeah, probably Thursday. I don't think we want to start talking about contravariance for 10 minutes, do we? Okay. Yeah. Well, this side is like, yes, and this side's like, no. So we'll start on Thursday. We'll get through contravariance, and we'll get through profunctors, and it'll be great. We have plenty of time on Thursday to get through both of those things. You guys are going to be amazing. Okay? Cool.